All right, it's 1:46 Eastern. Let's start back up. This will be my last module with all of you for the workshop. So before I start this, I'll say that it's been a pleasure working with all of you, and I'll be here for the rest of the workshop as well, working in the chat and in the hackathon as well. So hope to see you all there. For this last module that we're going to do, we're going to finish the entire cellularization of the ordinary differential equation model, and we're going to do that by implementing contact killing. And by contact killing, I mean cell death due to contact conditions between our local immune cells and our virus-releasing cells. Now, to go through and do that, we're going to cover a couple of new topics, specifically doing neighbor tracking in CC3D. There are lots of convenient iterators, some of which I believe have already been reviewed, but we're going to do some more with that. We're going to do some contact surface tracking, specifically using some of the functionality provided by CC3D for efficiently and conveniently getting the common surface area between particular cell types, or between specific cells, excuse me. And then we're going to do some very basic contact interaction modeling. We're going to see what that looks like mathematically. Not really spend too much time on it, spend much more time doing the fun bits, which is actually implementing it in CompuSol. Now we can start this off in a clean version using module _2.4 version 4. Again, this is provided in the student materials. I'm going to start by loading that in both Twedit and Player. So module _2.4 version 4. And then in Player as well. Make sure my simulation is stopped. Go to my modules, module _2.4 version 4. Give everyone a moment to get there. Okay. So let's begin. This is where we are. With the ODE model, we added no new cellularized terms when implementing chemotaxis. This is a purely spatial aspect of this model. So when doing cellularization with adding spatial information to an ODE model, certainly some aspects that are introduced that are purely spatial and are not represented explicitly in ordinary differential equations. Chemotaxis and random motility, certainly two of those things. Of course, you could probably argue that you could come up with correction factors and additional terms to add into the ODEs, but for a typical ODE model of something like viral infection like ours, this is not something that's typically explicitly represented, but rather is implicitly represented by our choices in various coefficients. Now for contact killing, the biological events that we would like to model with this, and by this what I mean is that immune cells that come in contact with virus-releasing cells, they're going to kill the virus-releasing cells. And biologically, what this looks like is that an infected cell will present antigen that's specific to a pathogen that's infected it. And the immune cells that show up to the site of infection, which are called cytotoxic T cells, these T cells during proliferation and recruitment and all of those processes that we represented in our lymph node model, those T cells are programmed to recognize that antigen. And when it does recognize that antigen, it'll then latch on to the infected cell that's presenting the antigen, and then through various interactions at their contact interface will induce apoptosis in the infected cell. So to complete our ODE model, we have one last term. And this entire module is just dedicated to implementing this last term in the ODE model, which is death of virus-releasing cells due to interactions with our local immune cells. Now, we're going to say in our model, in our cellularized model, that all of that death is due purely to contact killing. With different representations, you could perhaps say, write some different expressions for, say, release of reactive oxygen species by something like a neutrophil. But for our model, in the simple case, we're just going to say that all of our local cells they perform all of this killing of virus-releasing cells due to contact interactions. Now, to do this, we're going to first need to go through and do efficient calculation of interactions between cells that are neighbors, meaning that they're in contact. Now, you can do this the long and hard way, which is to go through and iterate over, say, every pixel in every cell, and then look in its neighborhood and figure out which cells are near a particular cell of interest. CompuCell will actually do this for you automatically and efficiently. It's quite fast, using a plugin called Neighbor Tracker. So if we go into our XML, Glacier model.xml, again, I'm working in the module 2.4 version. So if you're following with me, I'll give you some line numbers for references as we do this. I'm going to go down to where I added Pixel Tracker in module 2.3, and I'm going to make a little space, get an empty line in the XML. I'm going to use a code snippet to get Neighbor Tracker. It's a one-line entry for what we're going to use. So if you'd rather do it manually, the code snippet is shown on the left-hand side of my screen. To use the code generator and Twedit, you just go to the menu bar and CC3D ML, plugins, Neighbor Tracker. CC3D ML, plugins, Neighbor Tracker. Code snippet will have a couple of lines. The code snippet I have on the left-hand side of my screen is a single line entry. Either will work. As I warned you, I think yesterday, I like nice, clean code. I'm going to reduce mine to a single line. But again, either will work. And now Neighbor Tracker will be running in the background in CompuCell. And this is going to make available useful neighborhood information, provide some iterators to do efficient and fast neighbor interaction calculations. So if everyone's here, let's survey how we're actually going to do this. Now, again, the model that we're actually going to implement, according to the ODEs, is that virus-releasing cells are killed due to contact interactions with our local immune cells. And the way that we're going to spatialize this is that we're going to make that rate proportional to the ratio of contact area between a virus-releasing cell and an immune cell, the ratio of that contact area to its total available contact area. So this is an expression that's derived using the cellularization method that we continue to sort of wave our hand past. The probability expression that we're going to use is going to be another Poisson distribution shown here on the right. This is the same model parameter from the ODEs. We've got some scaling coefficients that we're going to implement. And then we're going to calculate the total contact area between one of our virus-releasing cells and some local immune cells. We're going to divide that by the total contact area of our particular virus-releasing cell of interest. Now, once we make this calculation, we'll then calculate the corresponding probability of killing a virus-releasing cell, and if our test passes, then we're going to implement cell death. So let's do it. Let's go to Glazier model steppables.py. We'll be working in Python. Let's go down to the step function of our steppable. The provided code starts at line 256. Now, at around line 261, this begins the section for killing by virus. Now, before that, let's implement contact killing. So let's make a little space before viral killing. And let's annotate our new section with a comment. Let's just say step, and then immune cell killing. This is the section of the step function where we do immune cell killing. Now, according to our equations, we use a model parameter from the ordinary differential equation model. The symbol for that coefficient was DEI2. Let's go ahead and retrieve that from the ODE model. In the final code snippet is on the left-hand side of my screen. You can refer to that, or you can follow along with me. I'm going to retrieve this value and put it in a variable called DEI2. We can get that from the ODE model using self.sbml.ode model. And you can get the parameter value for DEI2 using the key DEI2. And then the scaling that was mentioned but not explained. I'm going to scale this by time and by volume using our scaling coefficients multiplied by self.scale by time and divided by self.scale by volume. Now, one of the other values used in this calculation, due to scaling, is the total number of epithelial cells in the simulation. Now, this is just a generally useful calculation, so I actually put in the code snippet to put this at the very beginning of this step function. You don't have to do this so long as it's somewhere before the work that we'll do after this slide. I'm going to do this up at the beginning of the step function in case future development maybe uses this calculation in a location before where we're working now. So I'm going to add a line. If you're following in the code provided, you'll notice that the field secretors have been moved to the top for the exact same logic as why we're putting this calculation here. I'm going to declare this in a variable num underscore ECs for number of epithelial cells. I'm going to use the function cell list by type. I'm going to pass all 4 epithelial cell types, uninfected, infected, virus releasing, and dead. And then use the Python function len to get the length of that. Now, the length of that is the total number of epithelial cells in our simulation. So num underscore ECs equals LEN for length self.cell list by type. There's a code snippet generator, again, in CC3D Python, and then visit all cells of given type. That'll do some of this typing for you. And then we're passing all 4 cell types for epithelial cells, self.all caps uninfected, self.all caps infected, self.all caps virus releasing, and self.all caps dead. Question in the chat, what is the working principle of determination of the killing probability by the ODE rate equation? This is an excellent question that I would love to talk for hours about. But at a very high level, we're taking the same phenomenon and writing effectively 2 different mathematical representations of it. Now there is a way to relate how the ODE expression, there's a way to relate how it describes contact killing in the context of a well-mixed system, which is the ODE model system. There's a way to translate that expression into a mathematical form that is compatible with the structure of our model, which is that we have explicitly represented discrete cells that have explicitly described locations. We have explicitly represented contact interfaces, at least in the sense of the cellular POTS model and the context of this simulation environment. And at least in theory, if the relationship is right, when mapping the well-mixed expression from the ODE model to the heterogeneous expression, we should find that the emergent behavior of this system is approximately the same as the well-mixed results. I'm not sure if I can explain it well, I would say, in less than 15 minutes. So I'm going to, besides that, defer and say that feel free to email me, or we can discuss this during the hackathon. We can certainly discuss this at greater length. Now, back to our coding. We've got our number of epithelial cells that will be used in our calculation. We put that at the top in case future work wants to use that calculation as well. We have our DEI2 parameter from the ODE model. And we're going to do this algorithm of contact killing, considering every virus-releasing cell in our simulation. Every virus-releasing cell can potentially be killed by contact killing, so let's start a for loop. We'll do a loop iterating all of the virus-releasing cells currently in our simulation. Again, there's a code snippet for this, CC3D Python, visit, all cells of given type. Can erase all of the informative comments that are automatically added. And for our cell list by type, we're just going to pass self.virus-releasing, all of our virus-releasing cells. And return, make sure you're at one level of indentation up. Now, if everyone's with me, let's implement this. Now, in our calculations, one of the inputs for our probability is the ratio of the total contact area of our virus-releasing cell with immune cells to the total contact area of the virus-releasing cell in general. So we'd like to calculate these two values, iterating over the neighbors of our virus-releasing cell. So let's start two new variables, one being the total contact area of this virus-releasing cell with local immune cells. We'll call that variable CD8_area. We're going to set that to 0, and we're going to look in the neighborhood of our virus-releasing cell and accumulate surface area into that variable. And let's do the same for the total contact area with the variable surface area. We'll call it SRF_area for surface area. And we'll also set that equal to 0. So in the loop over our neighbors, we're going to look at our neighbors and accumulate contact area into these two variables. Now let's continue and let's start building our loop. We're going to do a loop over the neighborhood, or rather the neighbors of our virus-releasing cell. And by neighbor, what I mean is all of the other cells in simulation that are currently in contact with our virus-releasing cell. And we can do that with this function getCellNeighborDataList. This is a function provided by CompuCell. There's a code generator for it in TWedIt, CC3D Python, visit cell neighbors. CC3D Python, visit cell neighbors. Now this is going to generate 5 lines of code. First line is the start of our for loop. This is iterating over all of our neighbor cells of the cell that we've passed, as well as the total common surface area of that particular neighbor cell. So for each of these that are passed, we get each neighbor cell, including the medium, if the medium is in contact with our cell. So each neighbor cell in contact with our cell and the total surface area of their interface. So we can take this code snippet and we can just leave the start of our for loop for now. Make sure you have proper indentation in our for loop, and let's continue. Now we're going to use this common surface area and neighbor, and we're going to decide how we allocate the common surface area of the neighbor to our particular total surface area calculations. Again, we want the total surface area with immune cells and the total surface area in general. And what we're going to say is, first, that the total surface area available is just the common surface area with either our immune cells or the medium. If we have an epithelial sheet and we're interested in the contact area with an epithelial cell and something not in our sheet, well, since we have local immune cells in the medium in our second layer, then all of the common surface area when the neighbor is not an epithelial cell, when it's either the medium or an immune cell, that is the amount that will be added to our surface area variable. If the neighbor is the medium or an immune cell, then the common surface area will be added to our total surface area calculation. And this is shown here in the code snippet on the left for this first if block. We're going to test for two things here. First, we'll test if our neighbor is the medium. And again, in CompuCell, the medium is represented with the cell as none. So if neighbor is none. If the neighbor is none, then the neighbor is the medium. So if neighbor is none, or if our neighbor is an immune cell. That's the test for the total contact area. If the neighbor is the medium, so if neighbor is none, or if neighbor.type equals self.cd8 local, which is to say if our neighbor is the medium or our neighbor's type is our local immune cell. Then take our common surface area and add it to our total contact area, which is srf underscore area. So surf area plus equals common surface area. That's adding common surface area to our total contact area. Now to do a similar test to see if we're also going to add our contact area to the immune cell total area, let's start another conditional. Now we want to look and see if our neighbor's type is CD8 local. But the problem with this that we have to watch out for, and you can see this in the final code snippet on the left-hand side of my screen, the problem is that neighbor can be the medium, which means that neighbor can be none, and none does not have type. There is no such thing as none.type. So neighbor could be the medium, which is none, and there is no none.type, which means that in this next test, to see if our cell is a local cell, we first need to ask, is the neighbor the medium? And in fact, what we exactly want to say is that if neighbor is not none. So the next condition will only be evaluated if this first condition is true. So if our neighbor is not the medium and our neighbor type, neighbor.type is CD8 local. So neighbor.type equals self.cd8 local. And if both of those are true, then we'll add common surface area to CD8 area plus equals common surface area. So looping over every virus releasing cell and then looping over each of its neighbors. If the neighbor is the medium or of a local immune cell, then add the common surface area with this neighbor to our total contact surface area. Also, if the neighbor is not the medium and the neighbor's type is a local immune cell, then add the common surface area to the total contact surface area with immune cells, CD8 underscore area. Now, we can finish this for loop for the loop over the neighbors. Let's go down a couple of lines, and before we continue with actually implementing contact killing, let's just add a little easy performance improvement and say that in this cell loop, after having computed our contact areas, let's say that if the total contact surface area with CD8 local cells is 0, then continue on to the next cell. So if CD8 underscore area equal to 0, then just continue. Okay, now let's move on to our next step, and let's calculate our probability that this virus-releasing cell is killed due to contact interactions, which is proportional to these contact area calculations. So after our continue, let's go down and start the next portion of our calculations. Let's start by first defining the death rate. And this is a scaled version of the death rate from the ODE model. And that death rate, we'll declare this as just being named death underscore rate. And this is equal to the expression as shown up here in the top right of my slide that's currently on my screen. The death rate is equal to DEI2 from the ODE models times, and then we have one scaling coefficient, the number of epithelial cells, and then the ratio of the total contact area with local immune cells, or CD8 area, divided by the total contact area, SRF underscore area. So death rate equals DEI2 times the number of epithelial cells times total contact area with local immune cells divided by the total contact area. Now, using the Poisson distribution, calculate the probability of death. Call this variable PR underscore death for probability of death, and that equals 1 minus math.exp negative death rate, according to the Poisson distribution shown on the top right. And then lastly, let's just start our test for whether or not this cell dies. We have our probability. Let's start a conditional. Do our test by rolling the dice. We'll say if random.random, uniformly distributed random variable in 0 and 1, if random.random is less than our probability of death. Now, whatever happens in here is what will be executed when our cell dies of contact killing. Now, last step. Let's implement cell death. It's maybe automatic for some by now. I've done this a couple of times. First things first, our virus-releasing cell now becomes a dead cell. Cell.type equals self.dead. And secondly, and this is purely for good practice, and these epithelial cells are frozen, so a target volume is not necessary. But if someone were to come along and say unfreeze those cells in future work, you can save them one line of code and extra work they'd have to do and just say self.target volume equals 0. Okay, so I'll give everyone a minute. At this point, you can now switch over to player. You can do some quick checks for syntax errors. I'm going to do that. This completes our contact killing implementation. Before we proceed, I'm going to go to player, make sure my simulation is stopped. Just going to hit step, see if I get any syntax errors. No syntax errors. Okay. Now let's continue. I'm actually going to skip this exercise because I would like to progress a little farther into this. So the slides are available in the student materials. This is labeled as module 3.1. So would recommend that on your own, after maybe later today or after the workshop, make a note to go through and do this exercise. This is for single T cell killing, so placing another immune cell into the epithelial sheet or on top of the epithelial sheet, and then observing contact killing. Instead, I would like to finish this code and then wind this thing up together and watch it work. So last thing that we're going to do, got to update our plotting and tracking of death mechanisms. So we have two mechanisms of death now. Cells can die two ways. The first was with viral killing, which is the next section after where we're working. So now we have immune cell killing, and then immediately thereafter viral killing. Let's very quickly add tracking of contact killing. Now, if you recall from previous modules setting some of this up with Josh, we defined a dictionary in the initialization function of our steppable. The dictionary was called DeathMech. This is a dictionary tracking the death mechanisms in simulation. Depending on the state of your code, you may want to check this. Your death mechanism dictionary may or may not have an entry for contact killing. In the provided code, it's at line 25. It is not provided. It is not currently tracking contact. So if that's not there in your death mechanism dictionary, go ahead and add it. I'm going to add it with the key contact. So self.deathmech should have the keys viral and contact, and both should be initialized as 0. Now, once you've made sure that your death mechanism dictionary has the key contact, let's go back down to our contact killing calculations. The provided code, it should be around line 282. Now let's go into our implementation of actual killing. So when we kill the cell, here we're going to add to our death mechanism tracking our key contact. This value contains the current number of cells that have been killed due to contact killing. Just as we tracked viral killing with Josh. Now here, we're going to do the same thing. When a cell is killed by contact killing, we're going to add one. So self.deathmech, key contact, I'm going to add one to it. And then after that, let's add it to our plot. Should be just above the provided code around line 252. I already have plotting in the death mechanism window for viral. Let's add to that. You can just grab that line and copy it and fill it out. Give it the name contact. Say maybe make it green, just like our ODE plot. So now we'll be plotting viral death and contact death according to the spatial model. And now let's add the data point back down to our contact killing calculations. Provided code, it should be around line 284. Just before the viral killing step, let's make a little space. So this is outside of the loop over virus releasing cells. This is going to be just a post-processing sort of step. We're going to add our data point for contact killing. Let's add a comment to annotate that and say plot contact death data. And you can plot it for 0 values of contact killing or not. It's my preference to only do this when the contact killing count is greater than 0. It's not necessary by any means, but that's what I'm going to do. I'm going to say that if self.deathmech key contact is greater than 0, and then add my data point. There's a code snippet to generate this. I don't remember it off the top of my head. I'm just going to follow my code snippet. So the death data window, self.death data win. Function to add a data point is add underscore data underscore point. The name of our plot is contact. We're plotting this in units of days, so MCS times days to MCS, and then we're going to plot the value in our dictionary for contact killing, self.death underscore mech key contact. Again, the if statement for if the death mechanism contact killing is greater than 0 is by no means necessary. What is necessary is what I have at line 288, which is to actually add the data point. We're going to compare that to the ODE solution. Now, if everyone is with me, we can do a quick syntax check. Go back over to player, make sure our simulation is stopped, and then hit step. Check for errors. I received none reported. If you did, give everyone a minute to work out any typos. All right. Now, if you have CC3D successfully doing a step without any errors being thrown, then this model is done. Everything about that ODE model has now been cellularized. Everything has been successfully scaled to and from the ODE model and the spatialized version using a compartmental model, and everything is now set up to plot from the spatial model and the original ODE model to compare. In which case, I'm going to give you a couple of minutes to run it. So just go to Player, make sure you have all of your data plots. I'm going to maximize my player. I have all of my chemical species being plotted. I have all of my population data. And so long as dots show up for my contact killing, once immune cells show up, then all of that concerning data tracking is all implemented. I see here, comparing with the viral killing, that seems to track pretty well. It's a bit of a delay. In this particular case, the spatial model is a little early. This is completely acceptable when comparing a stochastic model like our spatial model to an ODE model. So there's then a corresponding earlier rise in the infected releasing cells. The virus releasing cells will rise a little earlier this time. There's some early stochasticity with the virus releasing cells, but that's, or with viral death, that's tracking better now with greater numbers. You see, we've got contact killing coming in early. I've got 2 immune cells in my replica. They're at the top left of my simulation. And then I look in my epithelial sheet, and what do you know? Got 2 blocks of dead cells. Now, just like what I saw with viral death, very early on, for very low values of viral killing, the spatial model had death before the ODE model started really showing values, and then it's kind of aligned once that's progressed a bit more. See the same thing with this spatialized version of contact killing. Josh touched on this yesterday about the distinction between continuous quantities and discrete quantities. The ODE model, in the ODE model, it is perfectly possible and fine and well to report a total number of cells killed by contact killing of, say, 0.1. Because the ODE models don't do discrete counting like we do here. We have discrete cells, and these numbers that we're reporting are from actually going through and counting how many of each cell type there is, how many actual discrete occurrences of contact killing there was. In which case, lots of where the deviations really come from when comparing the spatial model to the ODE model, much of that arises due to the differences in how counting is done in the first place. Can you or can you not count partial cells? Now, hopefully, you got some contact killing showing up in yours. I definitely have it showing up in mine. And if you haven't gotten it to work and don't feel like fighting with it, then you can just use module, it'll be underscore 3.1. That will get you to exactly where my code is now, doing exactly this. So if you're not here and you don't feel like fighting with it, just skip ahead and load module 3.1. Now, I'm also going to leave this exercise for you to do in your own time, because this, at least in my experience, this is an exercise that can eat up your entire night just out of pure intrigue. And that has to do with a specific deviation of the spatial model from the ODE model. Specifically, you'll notice that, look at most of these comparisons with the spatial model to the ODE model, so that this, other than early effects, and again, running another replica, it's just as possible to find the spatial model being a little bit behind the ODE model. So this, again, perfectly acceptable. But looking at the long-term behavior, this certainly tracks quite well. The one thing you'll notice is that with these deviations, with contact killing, not so much with the viral killing, there are lots of spatial mechanisms that are affecting how well these track that don't directly or can't really be directly derived from the ODE models. We played with this a little bit with changing the diffusion coefficient of the virus and seeing how that affects the rate of infection. You make the virus more or less diffusive, and you'll see, as I believe Josh pointed out, you see changes in how well, say, the infected and virus-releasing cells will track with the ODE model. The reason this tracks as well as it does right now is because we went through and manually calibrated parameters to where this fit at least well enough to be what you would call acceptable. Now, concerning things like contact killing, there are a lot of mechanisms that affect what immune cells do and how they get to where they're going. We've introduced chemotaxis. That chemotaxis of immune cells is due to the cytokine field that is secreted into by the virus-releasing cells, which means that you can change how much contact killing, how much more or less it can occur due to immune cells being able to find infected cells in the first place. Most interestingly, in my opinion, and I want to save it for all of you to do on your own time, is preferential attachment. Now, if we go back to our XML, we go to the contact plugin. In the provided code, it should be approximately around line 33. You'll notice that in the code that we distributed for module 2.4, and I think in a few earlier versions, that when we went through and initially did contact, I recommended that you just leave all of these values to 10, meaning no preferential attachment. Now, what I've uploaded this as is with an actual differential adhesion scheme. So when you go through and look at these, you'll notice that some cell types have lower or higher adhesion parameters. And specifically, you have CD8 local cells, all of our local immune cells. These are all set to values of 20. Every CD8 interface with another cell type. These are all set to 20. So the CD8 local cells, as it's currently set, have no preferential attachment to anything. The exercise that I would like for you all to explore, you can just do this very quickly, just as a first run of it. So go to the interface between virus-releasing cells and CD8 local cells and set that to something like 5. Meaning that the CD8 local cells have a preferential attachment to virus-releasing cells compared to infected cells and even uninfected cells. Now when you run this, and I'm just going to start it, and with no intent to show anything interesting, because if you run this on your own, you'll find that this should speak for itself. What you should find then is that there's a sort of instability that can drive immune cells to move much faster around the epithelial sheet due to this preferential attachment. And the way that that works is that immune cells kill by contact, but when they kill by contact, they change the type of the cell that they're attached to. If they're killing a virus-releasing cell, that virus-releasing cell then becomes a dead cell. Now, if the immune cell has preferential attachment to the virus-releasing cell, and suddenly the cell that it's killed is no longer a virus-releasing cell, then the immune cell will be sort of obliged by differential adhesion to latch on to another nearby virus-releasing cell if it's available. Running out of time, so again, I'd like to leave this exercise with all of you because it does take a little bit of time to get immune cells in here and so on and so forth, and I would really like to see us get to some of the other modules scheduled for the day. So I will leave you with that, and I will turn this back to James, and I think we are scheduled to break for lunch now.